Okay, so in this problem we have a slot, which makes things interesting. And we're also told that body D has a clockwise angular velocity of 1.5 radians per second, and we're told that the slot is parallel to OC in this case, and we're asked to determine the angular velocity of AOB, right? So the angular velocity of this body, basically. So cool. The only information that we're given is that this thing, body D, has this angular velocity, and we're just given a bunch of dimensions, right? And yeah, so what we need to do is we need a point that's going to relate the motion of body D to the motion of this whole thing, right? And in order to do that, we're going to construct a new point on the same point as point A, right? But take note that this point is actually on body D. It's not on this thingy over here, right? So I'm going to call this point E, okay? And we're going to use that to help relate the motion of body D and AOB, right? So the first thing that I'm going to do is I'm going to write the relative velocity equation that will help relate the velocities of those 2 points. So I'm going to say VE is equal to VA plus VE relative to A. Now you could have done it the other way, said VA is equal to VE plus VA relative to E. It's up to you. But yeah, we're just going to do it like this for now. And cool. So because these 2 points aren't on the same rigid body, remember point E is on body D. It's at the same position as point A, but it's on body D, right? And you might be thinking like, oh, there's a slot. How can it still be on body D? It's not really, it's like a fake point, if that makes sense, right? So if there was material here, right, at point E, then we're asking the question, what velocity would that be moving at, right? There doesn't have to be material at that point, right? So we could have even extended a whole line out to this point over here, right? And let's say this is like a whole meter away from the origin, and we could analyze the velocity at this point, pretending that it's attached to point D. Doesn't really matter, right? So there doesn't really have to be material at that point for us to analyze what the velocity would be over there. So yeah, hopefully that makes sense. Yeah, so point E and point A aren't on the same rigid body, so we can't break this up into omega, what would it be, EA crossed with R, E relative to A, purely because this thing doesn't exist. There's no thingy, angular velocity between point E and point A, because they aren't on the same rigid body, right? So we can't do that. So we need another method then of trying to solve for the velocity. So we can get the velocity of E pretty easily. We can say that VE is equal to VC plus VE relative to C. We know that VC is 0, so VE is equal to omega EC, which does exist in this case, crossed with R E relative to C. Right, and this has a value of 1.5 in the K direction, right? So we can solve for VE quite simply, right? Our problem is VA and VE, so the relative between the two. So what we're going to do, we're going to use a vector triangle to try and solve for that. And then once we've got VA, we can then, just like the previous problem, we can then use that to relate to O to then solve for the angular velocity of this whole thing, right? So what I'm going to do is I'm going to use a vector triangle thingy, and yeah, we'll take it from there. So I'm first going to look at body D and draw the velocity of point E. So I have my slot over here and I have point E over here, right? And then I have point C, and then this is the line that connects the two. So since this thing is going through fixed axis rotation, right, since this thing is going through fixed axis rotation, I know that the velocity of E needs to be perpendicular to whatever this vector is. So I know VE is going to act in that direction. Cool. So I'm sorted with VE in terms of getting its vector, and then we're going to look at VA next. So just next to that diagram, I'm going to draw O and A, right? I can draw this, but it's not really going to make that much of a difference, right? So this is point O, and then this is point A, and I know that VA is either going to go up or it's either going to go down. Intuitively, it's probably going to go down, but let's assume that we don't know, right? And we'll figure it out as we go along. So this is VA, and because it's going through fixed axis rotation, because this whole thing is going through fixed axis rotation about point O, right, VA has to be perpendicular to OA, right? Cool. And then we have V. So we've solved, or we've done as much as we could for VA, right? We don't know if it's going to point upwards or if it's going to point down, but we know that it's going to be perpendicular to this. So yeah, we've done as much as we could there. Now we need the relative velocity term. So when dealing with slots, the relative velocity will always be parallel to the slot, provided that you've drawn your points in the way I did over here. So point E is directly above point A, but on the other rigid body. If that's the case, then the relative velocity will always be along the slot, right? So the relative velocity could be pointing to the left or to the right, and this is going to be V E relative to A. Okay, and then I'm going to construct my triangle using all these vectors, right? So I'm going to start with my little phrase, I guess. So from left to right, VE must start at the tail of VA and end at the head of VE relative to A. So I'm going to draw in VE first because that's the vector I know the most about. I know both its direction and, that it's perpendicular to this line CE, right? So I'm going to draw in VE over here, and then the next vector I'm looking at is VA, and I know that VA, or VE rather, must start at the tail of VA. So VA is there, and then it could either go down, could either go up, right? So that's VA, that's VA. And then VE relative to A must end. So VE must end at the head of VE relative to A. And VE relative to A could either go left or right. So to close the triangle, I'm going to work on this side only. I'm going to ignore this side because if I draw it here, there's no triangle that's closed. So I need to draw it here, right? I'm just going to extend this further so that it actually connects. And then the relative could either go this way or that way. But I know that VE must end at the head of VE relative to A. So I'm going to choose it going this way. Okay, so this is VE relative to A. Cool, and I have my triangle. And then the next step is finding angles, and we need to first find a vector that is either horizontal or vertical. So we have a horizontal vector, which is VE relative to A, and then I'm going to draw two angles with the vectors close to it, if that makes sense. So I'm going to call this angle beta and this angle alpha, right? Cool. Then I need to find the angle that VE makes with a horizontal line from our diagram, and I need to find the angle that VA makes with a horizontal line from our diagram, right? So since this is an obtuse angle, I might want to do this where I just extend it, and then let's call this alpha prime, right? So from our diagram, we might only be able to get alpha prime, and then we can relate that to alpha by using angles on a straight line. So yeah, just doing that in case, just so that we have an extra visual clue to help us solve for the problem. Cool. Then I'm going to go into my diagram, right? And I'm going to see if I have any triangle, any big triangle that I can use to get the angles of and then relate to the angles between the vectors. So I have this line over here going like that, and then I have this 80 millimeters. So kind of look for dimensions. I have this 160, which represents this line over here, and then I have this 80, which represents the height. So I could probably do this, and I have this entire length over here, which makes a full triangle. Problem is that I don't have this entire length, right? But that's fine. For now, that's okay. I can find this angle here. I'm going to call it theta, right? And what I first want to do, I want to look at the vector VE. So I know that VE is going to be perpendicular to the line CE. So I'm going to draw that line in. So from C up to E, and I'm going to draw in the vector VE, right? And I know that this is going to be perpendicular, right? The angle that I'm looking for is beta over here, and that's the angle that VE makes with the horizontal line. So I'm just going to draw in a horizontal line at the head over here, and this is our beta. So this is the angle beta that we're looking for. Okay, now if you zoom into this section over here, you can see that we have a small little right angle triangle. So I'm just going to draw that in. Right. And then that's beta. And then over here, I have the line CE. Right. And then if I look at this region, I have another triangle. So in this region over here, this region here represents this region over here, right? So I have the height of 80, which is the height of this triangle. So this is 80, right? And I know that this is 90 degrees. So in order to get beta, I could probably get this angle over here. Let's call that phi. I could get phi, and then I know that 90 minus phi will give me beta. Cool. So in order to get phi, I would need to get this angle over here. Let's call that phi prime. And in order to get phi prime, I would need another dimension. So right now I've only got 80. I would need to get this bottom dimension here, which I'm going to call x. I'm going to call it x over there, right? But according to my trig, I know 160, I know 80, and I can use that to get theta, right? And then 160 cos theta will give me this entire length, right? And then 80 minus that will give me just this portion, right? So this 80 minus the entire length will leave me with this portion, which I've labeled as x. So x is equal to 160 cos theta, which theta is this angle over here, right? Subtracted and subtract 80 from that, right? That will give me x, and theta is equal to arctan of, no, not arctan, arcsine, 160 over 80, if I'm not mistaken, right? So solve for theta, then you can solve for x, and then substitute x here, and then you can use arctan to find this angle here. Let's call that psi or whatever. So psi is going to be equal to arctan of 80 over x, and then 90 minus psi is going to equal to phi prime, and then we know that 90 minus phi, 90 minus phi prime, sorry. So 90 minus phi prime is equal to phi, and then you substitute that here. So it's a long process, but yeah, I hope that kind of makes sense. And then yeah, you'll find beta. Cool, that's one angle down. Let's try and find the next one. So we're going to use the same approach, right? Where we draw our vector on our diagram, and then we use hints from our diagram to try and solve for the angle. So the angle that we want is the angle that VA makes with the horizontal line. So I'm going to draw in VA. I know that VA is perpendicular to the line AO. So that's VA, right? And I'm going to draw in our bigger triangle that we have before, just because we solved for theta and we have an angle that we can work with already. So let me draw in theta over here, right? And yeah, so I have theta, right? And I know that this is 90, so I can immediately get this angle over here, right? I've called this angle alpha. So let's try and see where alpha is, right? I know that I'm referencing a horizontal vector to draw the angle alpha, so I'll draw in a horizontal line for that. So there's my horizontal line, and then alpha is going to be this angle here, right? But I'm going to draw in our alpha prime over here, right? Cool. Now we're going to use the same procedure as before. So we're first going to try and get this angle here, then we can use sum of angles in a triangle to then solve for alpha prime, and then we'll use angles on a straight line to then solve for alpha. So theta, let me call this angle here, I'm just going to call it psi. So I know that psi is equal to 90 minus theta, and we've solved for theta. And then I'm going to call this angle here, I'm going to call it phi. And I know that phi is equal to 90 minus psi. Cool. And then to solve for alpha prime is equal to, again, 90 minus phi, and then alpha is equal to 180 minus alpha prime. Then you've got all these angles, you've solved for that angle, you solved for that one, then you can use your either sine rule or cos rule, probably sine rule, yeah, because you've solved for VE. Remember, we solved for VE by saying VE is equal to V, was it C? Yeah, and C is a fixed point, plus VE relative to C. VC was 0, so VE is equal to omega EC crossed with R. And we know this is 1.5 radians per second, right? So we've solved for VE, and we just need VA, which we can solve for using this triangle, right? Cool. Then once you've got VA, you're going to say VA is equal to V. Oh, So VA is equal to VO plus VA relative to O. We know that VO is 0, so VA is equal to omega AO crossed with R, A relative to O. And we know this, we know that we can solve for this.